Hey classes, welcome back. Check out the week 36. We're basically at the end of the school year. If you look at the lecture this week, it goes through Newton's laws of motion. We've had a little bit with Dr. Guccione coming in as a guest lecturer talking about the laws of motion and how it relates to some of the things that we've put together in our guest lecture classes like the Mars rover. And really, when you're looking at Newton's three laws of motion, you're looking at the basics of what you're going to do in physics in high school, physics in 8th grade. Physics is my personal favorite. Love teaching about and learning about physics. And let's jump right in, try and keep it to 10 minutes. This is your high school and college physics in 10 minutes. So here we go. If you look at Newton's laws of motion, the first thing I want you to have kind of in the back of your mind is Newton's laws are not the end-all be-all of physics. They work fantastic. They work for big things like figuring out the trajectory of a baseball, how high it's going to go, where it's going to go, things like that. They work good enough to get rockets and astronauts to the moon and space vehicles over to Mars. However, you might remember a guy we've talked about in this class by the name of Einstein. Turns out that Newton's laws work great for large things moving in everyday scales. When you start talking about things moving very, very quickly towards the speed of light, things like that, not so great. In other words, we have to kind of get the laws of the big and the laws of the very small and the very fast to talk to each other. So physics is not done by a long shot, but Newton's three laws are really the basis for everything you're going to do. So let's jump right in. First of all, in physics, we represent force with arrows. That's really, really useful. And when we're talking about forces, forces are kind of a weird thing when you really, really think about it. It's an invisible thing that's holding on to us, for example, right now. In Star Wars, you might remember when Darth Vader is going like this, he puts out his arm and he's got his force, right? In Star Wars, they can use Jedi can use forces to pull things and push things from a distance. And we all know, well, that's science fiction, that's silly. In other words, you can't really push or pull anything from a distance. How ridiculous would that be? But then you see something like this. This right here is a floating baseball. Now, think about what's going on here. Let me get a piece of paper, and hopefully this will work in class or in front of the screen here. But if I take this piece of paper and put it underneath the baseball, check it out. There's an electromagnet that's holding this baseball in place. It'll spin very, very slightly if I give it a little bit of a push, and I can usually get up here without breaking it. There it goes. It's still floating right there. It's an invisible force. Think about gravity right now. We can describe it. We can talk about what it is. We can very accurately describe the force of gravity that's holding you in place on the planet right now. Yet really having a picture of what that force is, we don't have a great picture of it. That's one of the things about physics I really want you to think about. Is what makes it so fascinating for me personally is we can describe these forces, but as far as, well, what are they really? It gets a little more difficult when you actually start talking about what is that invisible force that we're talking about. The three laws down at the bottom here are the ones that I'm asking everyone in the class to really commit to memory. We don't always commit everything to memory. Remember, science is about the process, but these three, yes, we want to commit them to memory. It's like your multiplication tables. There are some things that are very much worth committing to memory. We represent forces in nature in physics classes with arrows all the time. Now, when I first saw these, they call these free body diagrams. They call them free body diagrams because whatever it is that you're interested in, say this baseball right here, you want to talk about the forces that are acting on it. For example, it comes off a baseball bat, it's flying through the air. It's got friction acting to slow down its motion, the friction of the air that it's traveling through. We've got the force of the gravity pulling it down. At the moment it makes contact, say with a bat, it has a force against that bat and an equal and opposite force. We'll talk about those in just a second. The point is, one thing that I found very, very useful when thinking about forces when I was studying physics myself back in college was thinking about forces in terms of ropes. In other words, if you can imagine something being tied with a rope, if you can imagine, for example, gravity not just being as just an arrow on a board or in a diagram, but as an actual physical thing, holding you down. That is one of the things that I want you to think about when you look at these free body diagrams. These diagrams, when you're talking about what are the forces acting on an object in these pictures, because sometimes it can seem a little bit abstract when you're talking about, well, what are these arrows, where do they go? The cool part is that the math classes across the hall, when they're doing geometry, we can use the relative size of these arrows to talk about the sum of all the forces on an object. It's called vectors. It's a very, very cool thing. I personally loved it because it's very visual. You can say, oh, okay, I can tell by adding up all the arrows that are working on whatever it is I'm talking about. Again, say this baseball, you've got drag, lift, gravity, so forth. You can talk about the forces all combined and which arrow wins, if you will, which one will show you the direction that it's moving. So that's just a nice little handy thing. The first law is the law of inertia, which basically says that something staying in one place will tend to want to do that. Something in motion will tend to want to do this. This was the genius of Newton, actually. If you think about, for example, Aristotle, who we talked about way earlier in the year, an idea that he had was that things like to naturally come to rest. And it kind of makes sense. If I take this baseball and throw it across the room, I can guarantee that it bounced against the wall over there, came to rest, and is sitting on the floor right now. And here's the thing, it seemed to make sense to Aristotle, and it might seem to make sense to all of us. Yeah, you throw something, it comes to rest, things naturally want to come to rest. This was one of the things that was the genius of Newton. So let me switch the board here for just a second, I'll show you what I mean. Whoop. Board goes that way. Got a picture up here that comes from one of the most important books ever written in science, Principia. And in Newton's case, he drew a picture of a giant cannonball being shot around the world. Now, he probably would have used a baseball, but baseball wasn't around yet in the 17th century, so he used a cannonball. And here was the genius of Newton. If you took this baseball and you threw it hard enough that way, in other words, this way for me is north right here, as I take this baseball and wind up and throw it, if I throw it, my average fastball, it's probably dropped a bit in the last couple of years, say 50, 60 mile an hour fastball, it would go out and fall to the ground. Use your imagination for a second. Let's just say I could throw this baseball hard enough. Wait and wait and wait. Gonna wait a little bit longer. Wait. Got it. Check it out. It went all the way around the planet, came right back here. Why is that possible? If you think about the Earth as a sphere, remember it's a sphere. If you run into flat earthers, just say, hey, by the way, satellites wouldn't stay up if it wasn't a sphere. In the Principia, there's a famous illustration, a famous picture, and it's in your books as well, of a cannonball being shot around the world. And think about it. It's trying to fall, it's trying to fall, it's trying to fall, but the Earth, if you will, is curving away from it. So it's falling, but it's falling around the Earth. In the movie Gravity, when you see them supposedly floating, and I put floating in air quotes here, the characters, Sandra Bullock, who plays Dr. Stone, Kowalski, played by George Clooney, it looks like they're floating, but you got to remember, one of the points of all this is that we're learning that it's all relative motion. They are moving, compared to the Earth, thousands of miles per hour. Same with anything that's going around in orbit. There's no air to slow it down, very, very little at these altitudes that we're talking about, 200 miles up. So we're talking about free fall when we're talking about orbit. If you want to experience this for yourself, if you're on one of those rides like it's, say, Great America or Santa Cruz Beach Boardwalk, and you drop something right at the same moment that the ride drops you, it'll just kind of float in front of you for a second. They ask you not to do that, but physics teachers, you can't help but do that sort of thing. Also, the law of inertia is one of those things that you feel constantly. If you're, say, in a car and you're staying in one place and all of a sudden someone accelerates from a stoplight, you feel as if you're being pushed back in your seat. What's really going on is you're trying, because of your inertia, all mass has inertia, your body basically is trying, quote unquote, to stay in the same place. Think about, this is why I use the movie Gravity, think about movies where they don't get the law of inertia correct. Put on the glasses here. Once again, Star Wars example, the Millennium Falcon. If you are in a ship like this, and you always see in these movies the ship wants to zip off in one direction, right, near the speed of light. If you could really accelerate that fast, Han Solo looks at somebody and says, hey, we got to get out of here. We're being chased by the Empire. He punches it, they zip off. Think about the law of inertia in terms of you wanting to stay in the same place. you would, and everybody else in the ship would, be squashed into pancakes in the back of the ship as it jetted off that way. All right, moving on. We've got the second law, which is force equals mass times acceleration. This comes into play, for example, when we were talking about the dinosaurs being wiped out possibly by a large asteroid striking the Earth around 65 million years ago. You might remember we talked about Louis and Walter Alvarez over in Berkeley checking out there was some iridium dust, some iridium leftovers in one of the layers of sedimentary rock. Well, if you're talking about the amount of force it took to wipe out the dinosaurs, you've got a large mass, an asteroid about the size of a mountain. If you took Mount Everest and sawed it off at the bottom, that would be about that large, going at a tremendous speed, huge acceleration. When that struck the Earth, you've got a tremendous amount of force imparted on the Earth, enough where it threw up enough dust and debris that it probably, we think, wiped out the food chain by affecting the photosynthesizers. So force mass acceleration comes into play all the time. If you have just a huge acceleration in a tiny, tiny mass, think about in class we used a Nerf gun, fired a Nerf gun across the room. It's an itty bitty mass, but it's got a lot of acceleration. That's why if you get hit by a Nerf bullet, you're like, hey, ow, right? On the flip side, if you've got a tremendous amount of mass and a little itty bitty amount of acceleration, again, you can still have a huge force. The example we used in class was if a little Matchbox car was cruising down the street, and I said, it was going at 5 miles an hour, I said, hey, could you go out and stop that Matchbox car before it rolls into the street? You say, oh, no problem. You pick up your little Hot Wheel or Matchbox car. If, however, a steamroller lost its brakes, I don't know if steamrollers even have brakes, but if a steamroller lost its brakes and started rolling down a hill, it was going 5 miles an hour, I said, hey, stop that steamroller. You might not be so anxious to get out and try and stop a steamroller. Why? Mass and acceleration are multiplied. This is a product here. So in other words, if you have a big mass or a big acceleration, you have a huge force. If you have a huge mass and a big acceleration, you've got a tremendous force. And finally, the most quoted law probably in just everyday parlance and everyday language is action and reaction. For every action, there's an equal and opposite reaction. That gets again to our force diagram here. Action, reaction, you've got the most famous example, of course, being where in one of the classes we took a balloon, blew up the balloon, you let go of the balloon. You're letting, the action, of course, is the air being forced out one end. The reaction is, the reaction force is the rocket shooting off, or the balloon in that case, shooting off the other direction. So action, reaction, you hear that one all the time. We'll go into a little bit more detail on those, but your job was simply to get down the 3 laws. I wanted to give each of the laws a quick example. And I will see you online one more time. I believe we have one more video to do this year. Don't forget to take the Week 36 test. It's out there live online right now. And you've got to take it before Friday at noon because the gradebooks close for me Friday at 3 p.m. Take care, everybody. Have a great Week 36, and I'll see you online and in person now, which is awesome. Bye-bye.